Hello and welcome to lecture 5 of module 6. This is going to be the last lecture in this module. We are going to look at a couple of methods for numerical integration and finally summarize what we have done in numerical differentiation and integration in this particular module. Okay. Once when we apply the trapezoidal rule, let's say we want to find integral I is going to be integral from a to b f of x dx. Okay, and the area under the curve between a and b is what we want to find out. Okay, so what we can do is we can write our x1 equal to a and x2 equal to b and connect them with a straight line, and that becomes the trapezoidal rule. So our h in this particular case is just going to be equal to b minus a. Okay, so with h equal to b minus a, we will apply the trapezoidal rule, and the result that we will get, I is going to be equal to basically h divided by 2 y1 minus y1 plus y2, where y1 is f of x1 and y2 is f of x2. So I equal to h by 2 plus this plus negative f double dash of zeta divided by 12 multiplied by h cube. Okay, so this was our value of integral I when we computed the integral I as the area under the straight line joining these 2 points. Okay, so the area under the yellow curve was I. Okay, and I will just use a yellow chalk over here to represent the area under the yellow curve and call this as I of h to represent the fact that we have taken h equal to x1 minus x2, the entire region we have taken that as equal to h. Now let us consider another case where we have used the area, calculated the area as area under two different curves, first going from a to a plus b by 2 and then going from a plus b by 2 to b. Okay, so we will consider a midpoint of this, and that midpoint is going to be a plus b divided by 2. So in the red case we will have x1, x2 and x3. Okay, so in this case our area will be area under the red curve, which I will represent with the red hatched lines. Okay, and in that case I will write I of h by 2, h divided by 2, that's, or b by a divided by 4 is going to be our result. So h by 2 is because we have taken half the h, and we will call this as y1 plus y1.5, let us call that. So let us call this as y1, this particular guy we will call it as y1.5 and this as y2. Okay, so the first integral that is from going from y1 to y1.5 is going to be h divided by 2 whole divided by 2, because this is our new step size, multiplied by y1 plus y1.5 plus negative f double dash, let us call this as zeta 1 divided by 12 multiplied by step size to the power 3. In this case the step size is h by 2, so we will have h by 2 to the power 3. So that is, now what I have written over here is the first integral under the first interval. I will write down the integral under the second interval also, and that is going to be just h by 2 divided by 2 multiplied by y 1.5 plus y2 plus negative f double dash of zeta 2 divided by 12 h by 2 to the power 3. Okay. So, this is what we have as the two i's. Okay. Over here is the numerical approximation using h equal to b minus a, and the red box is the numerical approximation using h equal to b minus a divided by 2. Okay, and this is the overall error term and this is the error, also the error term. Okay. So, true value of integral is the numerical value plus the error. So, I will just drop the subscript from over here, and we know that this particular guy and this particular guy are going to be exactly the same. This we will write this as I of this we should be writing as I in bracket h, and this is basically I in bracket h by 2, not the previous notation. Okay. So, the numerical approximation is IH and IH by 2. So, I will just write down what those values are. I in bracket h is going to be equal to h by 2 y1 plus y2 is equal to b minus a divided by 2 multiplied by y of a plus y of b. Okay. So, that is going to be our IH. IH by 2 is going to be equal to h by 2 divided by 2 multiplied by y1 plus y 1.5 plus y 1.5 plus y2, which is equal to b minus a divided by 4 y of a plus 2 y of a plus b by 2 plus y of b. Okay. That is going to be our IH and IH by 2. The dotted boxes that we have over here, we will call them as errors EH and EH by 2. EH, we are going to write this as minus f double dash of zeta divided by 12 multiplied by h cubed, and E of h divided by 2 we can write that as minus f double dash of zeta 1 divided by 12 h by 2 cubed plus minus f double dash of zeta 2 divided by 12 multiplied by h by 2 cubed. Okay. At this point, what we will do is we will write f double dash of zeta 1 plus f double dash of zeta 2, that value we will write that as approximately equal to f double dash of zeta divided by 2. Okay. This is more accurate way of saying, rather than saying f double dash of, sorry, this not divided by 2 equal to 2 f double dash of zeta, sorry, that is a mistake. F double dash of zeta 1 equal to f approximately equal to f double dash of zeta, and f double dash of zeta 2 approximately f double dash of zeta. Rather than saying it in this way, a more appropriate way of saying is f double dash of zeta is approximately the average of f double dash of zeta 1 and f double dash of zeta 2. That is essentially what we are saying at this particular stage. So what we actually have is that f double dash of zeta can replace essentially this particular value when we add them up. So what I will do is I will write that as E of h by 2 is going to be equal to 1 by 12 multiplied by h cubed okay. So or let's so what we are actually going to do at this stage is this particular the values that we have over here, we will just write them that as equal to f double dash of zetas, and we will have a factor of 2 because these are the two values over here. Again there are approximations involved in that, so this is not an exact way of writing this these things down. So we will have this written as 2 or approximately equal to 2 multiplied by f double dash of zeta divided by 12 h by 2 cubed. Okay. So h by 2 cubed divided by 12 comes out of the bracket, and we will have minus of f double dash of zeta 1 plus f double dash of zeta 2, which we are writing as 2 times f double dash of zeta. I forgot the minus sign over there. So this is going to be our error in the computing the numerical derivative using h by 2 using the trapezoidal rule. Okay. So that is essentially what we are going to get at this stage. So we will write now the integral, the true integral okay. So the true integral integral a to b f of x dx is the same. As a result, what we can say is IH plus EH is the true integral is going to be equal to IH by 2 plus EH by 2. Which we will write that equal to some I true. Okay. Let us also write this particular constant f double dash zeta divided by 12 as some constant c. So let us write okay, or let us write negative f double dash of zeta divided by 12. As a result, we can write I true as equal to IH plus c times h cubed. Okay. We can also write I true as equal to IH by 2 plus, and if we go to this particular expression, it is 2 multiplied by c multiplied by h by 2 cubed, 2c h by 2 cubed, okay, which is going to be equal to I of h by 2 plus c divided by h cubed divided by 2 squared. Okay. So now what we will do is multiply this equation by 2 squared, multiply this equation by minus 1, and then add the 2. Okay. So we will get minus I true plus 2 to the power 2 I true will be equal to I minus IH minus IH plus CH cubed okay plus 2 to the power 2 IH by 2 plus 2 to the power 2 multiplied by C H cubed by 2 squared. Okay, so this gets cancelled, this and this also gets cancelled. So we will have, from this expression we can have 4 times I true minus I true equal to 2 squared I h by 2 minus I h is going to be our expression. Dividing throughout, we will get I true is 2 to the power n, sorry 2 to the power 2 I h by 2 minus I of h divided by 2 to the power 2 minus 1. Okay. This particular method of getting an improved value of I true is called Richardson's extrapolation. Okay. So the idea behind Richardson's extrapolation is this: any true integral I can be written as I numerical using the value of h plus some constant multiplied by the leading error term. So let us write that as constant C1 multiplied by the leading error h to the power n. Okay. Keep in mind that this we are able to write because of the this we are able to write because of the mean value theorem. Okay. If we go back and look at the expression that we have over here, E of h by 2 is not exactly equal to 2 times f double dash of zeta, but it is approximately equal to 2 times h double dash of zeta. Okay. So instead of that, if we were to write the entire series of rather than truncating it using the mean value theorem, if we write the entire series, we will get this as C1 h to the power n plus C2 h to the power n plus 1 plus so on. Okay. So this is what we will get using IH. If we were to use two implementations of the same method, we will have this as I using h by 2 plus C1 using h by 2 to the power n plus C2 using h by 2 to the power n plus 1. This one will be, this particular guy will actually have C1 h by 2 to the power n because of the first implementation, C1 h by 2 to the power n because of the second implementation. Okay. So that actually will get multiplied by 2. In other words, what we are saying is that we have I h by 2 is actually going to be written as I going from y1 to y1.5 plus I y1.5 to y2. Okay. And this guy is going to be I true plus C1 h by 2 to the power n plus C2 h by 2 to the power n plus 1 okay, and this is I true from 1 to 1.5 plus I true from 1.5 to 2 plus C1 h by 2 to the power n plus C2 h by 2 to the power n plus 1. Okay. So, this plus this is going to be our I h by is going to be equal to I true. Okay. This term plus this term will get added and we will get a factor of 2. This term and this term will get added and we will again get a factor of 2. That is essentially how the factor of 2 comes into picture over there. Okay. So, now what we can do is we can multiply this particular expression by 2 to the power n minus 1, and this expression we can multiply this by minus 1, and then when we add up we will get I true multiplied by 2 to the power n minus 1 minus 1 is going to be equal to 2 to the power n minus 1 I h by 2 minus I h. Okay, this is going to be the numerical integral plus this term and this term is going to get cancelled when we multiply this guy by 2 to the power n minus 1, because 2 to the power n minus 1 multiplied by 2 is going to be 2 to the power n, 2 to the power n and 2 to the power n is going to get cancelled. Okay, plus we will get C2 h to the power n plus 1 and a negative sign over there plus 2 to the power n multiplied by h to the power n plus 1 divided by 2 to the power n plus 1. Okay. So, this and this will get cancelled and we will have this the denominator as 2. Okay. As a result of this, when we divide by 2 to the power n minus 1, what we will get as the true I true as using Richardson's extrapolation, we will get this as I true as 2 to the power n minus 1 I of h by 2 minus I of h divided by 2 to the power n minus 1 minus 1 plus C2 multiplied by h to the power n plus 1 divided by 2. We will have this 2 factor that comes in, and then this is 2 to the power n minus 1 minus 1. So, we will have 2 multiplied by 2 to the power n minus 1 minus 1. This is going to be the Richardson's extrapolation. Okay. So, for trapezoidal method n was equal to 3. When we substitute that in this particular expression, what we are going to get is I true is going to be 2 to the power 3 minus 1, that is 2 to the power 2 minus I of h divided by 2 to the power 2 minus 1 plus error of the order of n plus 1. N was 3, as a result error is of the order of h to the power 4. Simpson's 1/3 in this case n was equal to 5. So, I true is going to be equal to 2 to the power 4 I of h by 2 minus I of h divided by 2 to the power 4 minus 1 plus order of h to the power 6. Okay, why h to the power 6? Because the Simpson's 1/3 rule is h to the power 5 accurate. We increase the order of accuracy by 1 while when we implement the Richardson's extrapolation, and likewise we can have Simpson's 3/8 rule, so on and so forth. Okay, if we iteratively apply Richardson's extrapolation, then we come to a special method of integration called Romberg integration. Okay. Beyond stating that, I won't go into the details of Romberg integration. You can look up any standard textbook for numerical methods and you will be able to see what Romberg integration means. Okay. So what do we do in Richardson's extrapolation is we obtain an integral under a curve using one single interval for the trapezoidal rule, or 2 intervals for the Simpson's 1/3 rules, or 3 interval for the Simpson's 3/8 rule. Okay, so that gives us the value of h in the 3 cases. H is going to be b minus a by 2 and b minus a by 3 respectively. Then we go on and use half that particular h value. So in case of trapezoidal rule, we redo the simulations, or we redo the calculations using 2 intervals. In case of 1/3 rule, we redo the calculations using 4 intervals, and in the 3/8 rule we redo the calculations using 6 intervals. Okay, so we will get I h by 2 as the result that we get using in this particular case 2 intervals, in this particular case 4 intervals. That particular value multiplied by 4 minus the previous integral value that we have computed using just one single interval is the numerator, divided by 3 is the denominator, and the new integral value that we are going to get is 1 order more accurate than either of our older integral values. Okay, so that is the idea behind the Richardson's extrapolation. Okay, so that summarizes our Richardson's extrapolation. What I will do very quickly is show one more way of deriving the trapezoidal rule, and then talk very quickly about another method called Gauss quadrature method. So we will derive using method of undetermined coefficients. Okay. In this particular case, in the method of undetermined coefficients, we will write I trapezoidal is going to be equal to a1 multiplied by f of a plus a2 multiplied by f of b. Okay, this is how we will write our a1 and a2. This is how we will write our I trapezoid. Okay. What we know with the trapezoidal rule is this: if our curve was a flat line and we wanted to find the area under this particular curve, so in other words, if our curve was a constant function, we know that the value that the trapezoidal rule gives us is going to be the exact value under that curve. Second case we also know is that if this was a line with unit slope, let us say y equal to x, and in this particular case the curve is y equal to 1, and if we were to find area under this curve between a to b, this area obtained through the trapezoidal method is also going to be exact. Okay, that is the property that we are going to use in order to use the method of undetermined coefficients. So the first case is if f of x is going to be equal to 1, then the trapezoidal rule is exact. In that case, I trapezoid is a multiplied by f of a, f of a is a1 multiplied by f of a is nothing but 1. So a1 multiplied by 1 plus a2 multiplied by f of b, we substitute x equal to b in this case, again f of x equals 1. So this is what we will get, is going to be equal to integral from a to b f of x dx, that is 1 multiplied by dx. Now this is going to be nothing but x going from a to b, which is nothing but b minus a. Okay, so a1 plus a2 is going to be equal to b minus a is our first equation. I'll just write this in a more descriptive form. Okay, our second equation is that for f of x equal to x, also the trapezoidal rule gives us the exact result. Okay, so we again substitute f of a in this particular case is going to be equal to a, f of b in this case is going to be equal to b. So the I trapezoid is going to be a1 multiplied by a plus a2 multiplied by b. Okay, that is going to be equal to integral from a to b f of x dx. F of x is x, so we will have x dx, which is equal to x square divided by 2. Going from a to b. Okay, so writing those equations down, writing both those equations down over here, what we get is this. So our first equation is a1 plus a2 equal to b minus a. Okay, this is our first equation. Our second equation is a multiplied by a1 plus b multiplied by a2 is b squared minus a squared divided by 2. Okay, so what we will do is we will multiply this equation by minus a and add these equations up. So we will get b minus a multiplied by a2 is going to be equal to b squared by 2 minus a squared by 2, this is what we get by writing here, minus ab, okay, plus a squared. Okay, so this is going to be b squared plus a squared divided by 2 minus ab, which is equal to b squared minus ab plus a squared divided by 2, which is b minus a the whole squared divided by 2. Okay, that is going to be equal to a2 multiplied by b minus a. So a2 is going to be equal to b minus a divided by 2, a1 is going to be equal to b1 b minus a minus b minus a by 2, which is equal to b minus a divided by 2. Okay, and substituting in this particular equation as a1 equal to b minus a by 2 and a2 equal to b minus a by 2, when we substitute this, we will get this as b minus a divided by 2 multiplied by f of a plus f of b, which is exactly what we had as the trapezoidal rule that we have derived using 3 different methods earlier, using the geometric method, using the algebraic method, and using integral of the Newton's forward difference formula. Okay, the new method that we introduced over here is method of undetermined coefficients, where the trapezoidal rule is taken as a weighted average of the function computed at the 2 endpoints. Okay, Gauss quadrature. Okay, compared to the Newton Cotes formulae, Gauss quadrature is an open method. okay, and it is specifically used to calculate integral from -1 to 1 of f of x dx. Okay, it specifically used to calculate this. Any integral a to b f of x dx can suitably be converted through a linear change of variable x into the form -1 to 1. So this is not a restrictive form, this is indeed a fairly general form of the expression. Okay, so the idea behind Gauss quadrature is this: is given an arbitrary function f of x, you want to find the integral from -1 to 1 f of x dx. What we do is we select n number of points within this interval, we select n points within this interval such that this integral is a weighted average of the functions computed at those n points. Okay, let us first consider the example as for n equal to 2. Using the quadrature method is going to be equal to some constant f1 multiplied by f of x1, or I will just write this as f of u1 to separate it out from x1, plus f2 multiplied by f of u2, where u1 and u2 are the two values within the interval -1 to 1. Okay, and our objective is to find a1, u1, a2, u2. Okay, and like we did in the trapezoidal rule, what we are going to do in the Gauss quadrature method is the same idea, is for f of x equal to 1, f of x equal to x, f of x equal to x square and f of x equal to x cube, we will say that the Gauss quadrature method should give us the perfect solution. Okay. So here I will write the true integral and here I will write the numerical integral. Okay, here, so this is going to be -1 to 1 f of x dx. This is going to be equal to a1 f of u1 plus a2 f of u2. Okay, in the first case f of x is going to be equal to 1. So integral from -1 to 1 dx is x from -1 to 1, which is equal to 2. Okay, it is 1 minus -1 equal to 2. When we substitute u1 and u2 in this particular case, we will get this as a1 multiplied by 1 plus a2 multiplied by 1. Okay, so that is going to be our first equation. The second equation is going to be for f of x equal to x. Integral from -1 to 1 f of x dx is x square by 2 going from -1 to 1, which is 1 squared by 2 minus of -1 squared by 2 which is equal to 0. Okay. In on to the right hand side, what we will get is a1 multiplied by u1 plus a2 multiplied by u2. Okay. The third case is f of x equal to x squared, and this we will get is as x cube by 3 from -1 to 1, which is equal to 1 by 3 minus of -1 by 3, which is equal to 2 by 3. That is what we get onto the left hand side, and to the right hand side we will get a1 u1 squared plus a2 u2 squared. Okay, f of u1 is going to be u1 squared, f of u2 is going to be u2 squared. So a1 u1 squared plus a2 u2 squared. Okay, and the fourth equation is going to be f of x equal to x cubed, and in that case we will have x to the power 4 divided by 4 from -1 to 1, which is equal to 1 by 4 minus of 1 by 4 which is equal to 0, and this is a1 u1 cubed plus a2 u2 cubed. Okay, so now we have the 4 equations, a1 plus a2 equal to 2, a1 u1 plus a2 u2 equal to 0, a1 u1 squared plus a2 u2 squared equal to 2 by 3, and a1 u1 cubed plus a2 u2 cubed equal to 0. These are the 4 equations that we need to solve. When we solve this equation, the value of a1 and a2 we get are 1, we will get a1 equal to a2 equal to 1, and u1 we will get as minus 1 by root 3, and u2 we will get as plus 1 by square root of 3. Okay. So 1 plus 1 is 2, minus 1/3 plus 1/3 is 0, minus 1 by root 3 plus 1 by root 3 equal to 0, 1 by root 3 squared plus minus of 1 by root 3 squared is 1 by 3 plus 1 by 3 which is 2 by 3, and this is going to be minus of 1 by 3 root 3 plus 1 by 3 root 3 which is equal to 0. Okay. So this is going to satisfy. As a result, the for the Gauss quadrature method, the final result is going to be integral from minus 1 to 1 f of x dx is going to be equal to f of square root of 1 by 3 plus f of square root of minus 1 by 3. Okay. This is going to be the Gauss quadrature results. Okay. So that is essentially the numerical methods that I wanted to cover for getting integral of numerical integral of any function f of x. What we will do now in the next about 10 minutes or so is recap what we have done overall for numerical differentiation and numerical integration in this particular module. So let us now recap the overall things that we have done for numerical differentiation and numerical integration. Okay, so the general setup for differentiation was that given a function y equal to f of x, we wanted to obtain dy by dx, okay, which is essentially the slope of the tangent at the desired point. Okay, that is the geometric interpretation of differentiation. We then saw that we can use a forward difference formula in order to get the numerical differentiation, and the line over here shows the numerical differentiation using the forward difference formula, and the red line over here shows the tangent to that particular curve, and dy by dx using forward difference was yi plus 1 minus yi minus 1 divided by delta x. Okay. Then the other possibility is to use the central difference formula. So to find the slope at this particular point, we will do the numerical differentiation between xi plus 1 and xi minus 1, and based on the central difference formula we get is dy by dx equal to yi plus 1 minus yi minus 1 divided by 2 times delta x, where delta x is this particular difference between xi minus 1 and xi. After that, what we did was we used the Taylor series expansion to find the numerical differentiation for various different conditions. So a summary of numerical f dash of x, we used method of characteristics where we write f of x plus 1 using the Taylor series expansion, f of x minus 1 using the Taylor series expansion, f of x plus 2, f of x minus 2, etc. as needed, and the differential of interest we will write that as df by dx as a weighted average of all these f of x. So in case of the central difference formula by df for df by dx, we write this as a1 f of x by a minus 1 plus a2 multiplied by f of xi plus a3 multiplied by f of xi plus 1. We substitute the Taylor's series in each of these f of x I minus 1, f of x I plus 1, we do not have to substitute anything for f of x I, and then we equate the appropriate terms. Based on that we will get the values of a1, a2 and a3, as well as we will get the value of error of the leading term that we obtained. Okay. Based on this we were able to we derived all these formulae. This is the forward, the backward and the central difference formula. The forward and backward difference formula, the truncation error is order of h, that is order of the difference delta x that we took. For the central difference formula, this is the actual formula that we derived, which is accurate to h squared. We finally derived a 3-point forward difference formula, that means it takes value of x I plus 2, I plus 1 and x I to compute f dash of x I, okay, and that again we found was order of h square accurate, and this was the overall expression for the numerical f dash of x. Okay. Then we also did the higher derivatives. The second derivative using central difference formula we obtained using the forward difference formula can be obtained in a similar manner. We did not do third derivatives and so on, mainly because they are not as used in chemical engineering. There are a few disciplines in chemical engineering which do use the third and fourth derivatives, but for the most part we are restricted to first and second derivative. As a result we just stopped at first and second derivatives, and this is the equation that we can use for the central differences for numerical differentiation. Then finally in the numerical differentiation we covered the trade off between round off and truncation errors. Okay. What we have shown earlier is just the truncation error part. Truncation error decreases as h is decreased. However, with respect to round off errors, the round off errors increase as h is increased. The red curve over here shows the truncation errors. As step size is decreased, the truncation error decreases. However, the round off error increases as the step size is increased. Okay, so the total error goes through a minima, and that minima happens at certain step size. For f dash of x, we had found that for forward difference method, h is the best h that we get is approximately proportional to the machine precision to the power 1 by 2, and for the central difference h is proportional to the machine precision to the power 1/3. Okay. In Microsoft Excel, machine precision is 10 to the power 16. As a result, h is approximately 10 to the power, sorry, machine precision is 10 to the power minus 16. So the h that we should use for forward difference should be of the order of 10 to the power minus 8, and the h that we use for central difference should be of the order of 10 to the power minus 5 to 10 to the power minus 6. Okay. So this is the numerical result that we had obtained. This is result from the Excel solving that we had done in module 3 itself, and we can see that the forward difference, the errors are always larger than the errors in the central difference formula. Okay. And 10 to the power minus 8 is the best h value for forward difference, and 10 to the power minus 5 is the best h value for the central difference as well as for the 3-point forward difference. Okay. Going to numerical integration, numerical integration is nothing but area under the curve between 2 points A and B. Okay. So this area of the shaded region is what numerical integration is really all about. How we do numerical integration is that we split that area into various intervals. They may be, they should preferably be equally spaced intervals, but there is no reason for us to choose equally spaced intervals. So we split the region into various intervals and add the areas under each of the curve. So for trapezoidal method, the way we will do it is we will keep calculating area for each trapezoid and progress as shown. Okay. So we will calculate the area for the first interval, second interval, third, fourth, fifth, sixth, and we will just add up those areas as we show in this animation, this plus this plus this, this, and this. We will get all those areas and we will sum up the areas under the curve under individual trapezoid, and that represents area under the curve. Okay. We used 3 different methods, the trapezoidal rule, Simpson's 1/3 rule and the Simpson's 3/8 rule, in order to compute the interval. The Richardson's method we said was for trapezoidal rule, it's 2 to the power 2 minus 1 divided by 2 to the power 2 minus 1, that was the for trapezoidal rule. For both Simpson's 1/3 and 3/8 rule, it is going to be 2 to the power 4 in this particular case, and the order of accuracy is h cubed for the trapezoidal rule, h to the whereas h to the power 4 for Richardson's rule using the trapezoidal solutions. Whereas when we apply the Richardson's rule for Simpson's 1/3, we will get h to the power 6 accurate, Simpson's 3/8 also will lead us to h to the power 6 accurate, okay. And this should have been n bar rather than n, where n bar is the value that we see over here. So it is 2 to the power n bar minus 1 and not 2 to the power n bar over here, okay. So that is the integration formula that we get using trapezoidal, the Simpson's rules, the Richardson's rule, and the implementation of trapezoidal rule for the PFR example that we had seen. The single implementation of the trapezoidal rule is to find the area under this particular trapezoid when we wanted to integrate from 0 to 0.9 dx divided by minus r of x, okay. Two implementation of trapezoidal rule was area under the orange curve. Clearly we can see area under this particular or pink or orange curve is significantly better than area under this light blue curve as the approximation for the true area, okay. The two applications of the trapezoidal rule will lead us to this particular area plus this particular area, okay. As against that, we have the single application of Simpson's 1/3 rule. We are going to fit a second order curve, okay. This particular curve is a second order curve that is fitted to these 3 data points, and area under the second order curve is what we get from a single application of the Simpson's 1/3 rule. Finally, Simpson's 3/8 rule is going to give us area under a third order polynomial that is fitted to this point, this point, this point and this point. So this is the third order polynomial that we fit, and the area under the third order polynomial is the result of single application of the Simpson's 3/8 rule, okay. And these were the comparisons that we had made in the previous lecture of this particular module. The volume of the CSTR, in each column we have the result using a single step size, and what we see is that the step size of 0.15 leads to 6 applications of the trapezoidal rule to get, so from 0 to 0.15, from 0.15 to 0.3, 0.3 to 0.3, 4.5, so on up to 0.9. So 6 applications of trapezoidal rule, 3 applications of 1/3 rule or 2 applications of 3/8 rule will give you these areas. The actual area is 6.226. The trapezoidal rule is further away from the true area compared to the 1/3 and the 3/8 rule. In this particular example, 1/3 rule is actually giving us better results than the 3/8 rule. Keep in mind, 3/8 rule is actually slightly more accurate than the Simpson's 1/3 rule, but the order of accuracy is the same. And we can see that h equal to 0.15 is already good enough for Simpson's 1/3 rule and the Simpson's 3/8 rule, but it is still not good enough for the trapezoidal rule. We need to go for one more step of the trapezoidal rule in order to get accurate results, okay. So that is essentially what we observe, and based on all these observations, these are the overall general guidelines for numerical differentiation and numerical integration. For numerical differentiation, this is what I do. As long as possible, I prefer to use the central difference method in general, as long as possible I say, because in certain cases it may not be easy or possible to use central difference rule, and choose the appropriate step size of h. So the central difference rule for f dash of x, I will choose h as approximately 10 to the power minus 6. Central difference for f double dash of x, I will choose h as approximately 10 to the power minus 4, okay, that is epsilon to the power 1/4. For numerical integration, what we said is we would prefer Simpson's 1/3 rule, because the accuracy of Simpson's 1/3 rule is h to the power 5. We will use multiple applications of Simpson's 1/3 rule to improve the accuracy, and we will use Richardson's extrapolation. It requires more computation, but it is effective. Usually I have found Simpson's 1/3 rule to be good enough for most practical examples of our interest. We choose smaller and smaller h values in order to get more accurate Simpson's 1/3 rule. And finally, Gauss quadrature is, it is an open method. In case of n equal to 2, we find the integral from -1 to 1, that is integral under this this blue shaded region. We will use that as a weighted average of f of x1 plus f of x2. For n equal to 2, we will get the value to be f of -1 by root 3 plus f of 1 by root 3. For n equal to 2, we will get 5 by 9 multiplied by f of minus root 3 by 5 plus 8 by 9 multiplied by f of 0 plus 5 by 9 multiplied by f of root 3 by 5, okay. So this is the result for Gauss quadrature. The advantage of Gauss quadrature is it is very easy to implement and it gives a fairly high order of accuracy. The disadvantage of Gauss quadrature is that it cannot be straightforwardly applied if we want to use multiple intervals for applying the Gauss quadrature, okay. However, it is a very good formula, and we have formula that is h to the power 12 accurate and h to the power 16 accurate also, that have already been pre-computed, and a standard textbook will give you these results. For example, Chapra and Canal has the results available for n equal to 2, 3, 4, 5 and 6, I believe. You can read up the textbook to get the idea of higher order Gauss quadrature, okay. And I will leave you with the general guidelines that we have developed in this particular lecture, okay. Thank you.